Okay, hello everyone. Welcome to another session of Solidity Bootcamp. I am Vaida and I am program manager for this bootcamp. I couldn't join you guys yesterday because I was on a flight, but really nice to finally meet you. Yeah, and really happy to be here with you and to join your journeys. A little bit about the attendance, since we got a question there. So the attendance is tracked, and we also track the amount of time you spend in a session. So that means that if you just come for 5 minutes, it's not going to count. So you need to attend at least 80 minutes of the session for the attendance to be counted. So if you have any questions, just drop them in the chat here or in the Discord, and I will answer them to you later. And also, I'm a person that if you have any problems, if you have any feedback, just need any sort of forum support, just reach out to me, and I will be very happy to help you. Okay, then let's start the session. And so then I will just give the mic to Lawrence. Over to you.
Hey, thanks, and welcome everybody. I hope you're having a good day. What I'm going to do is I'll share my screen and I'll turn off my camera because it tends to give my internet problems. So let me do that. Okay, so today is going to be another theory lesson, but yeah, tomorrow we'll get stuck into some solidity. So, but we need to get through a little bit of theory first. So let's do that. So we can start off. If anybody has questions from the first lesson, we can review those. And then we'll start to look at some of the blockchain components in a little bit more detail. I introduced them in a very sketchy way in the last lesson, so I'm going to start going into more detail about those this lesson. For example, we're going to look at some of the data structures. What do blocks actually look like? This will be a little bit abstract. It's we're not going to go into details about what the Ethereum blocks look like in detail in this lesson, but we will do it in a couple of lessons' time. Then we'll discuss consensus mechanisms and how block production happens and how blockchains come to agreement about the state of the system. And we'll finish off looking at a couple of areas which you may not have come across, but are quite important when you're thinking about blockchains. And these are the cryptoeconomics. So this is really how we guide behavior amongst participants in blockchain systems. And then governance, which is about how a blockchain can develop over time, and how decisions are made about how the blockchain works over time. Okay, as usual, please ask questions on Slido. There's also a poll there for people to, you can put in areas that you would like us to look at, and we'll take note of that. All right. At some point soon, we'll start to think about team projects. Typically, the last 4 weeks of the course, we'll set aside 1 day each week for you to work on team projects. But before then, it's a good idea to start to think about any ideas you may have around the project. If you don't have an idea, we can suggest some, and we can advise you on what would make a reasonable project. One bit of advice I would give up front is to keep the scope of the project quite small, because you don't have a great deal of time, so you're not going to have time to write a large project or do much in depth. And it's also good for keeping your interest up. If you're making progress, you can get something finished, that'll keep your motivation going, rather than trying to do something too large and only get part way through. Okay, let's just review a little bit. I'll go back to some of the topics we had yesterday. So I think something I didn't mention yesterday was looking at particular cryptography that's used in Ethereum and Bitcoin. I mentioned things like the digital signatures, but I didn't really say what this was based on and the cryptographic primitives behind this. And what is used in Ethereum is are things called elliptic curves. So these are curves, and they have that kind of equation, the y squared equals x cubed, etc. And if you plot one of these curves on the against the real numbers, you get that kind of shape. So it's quite a distinctive shape that you get. And this actually is slightly misleading, because where we use it in blockchains, we don't actually use real numbers. We use finite fields, which means we use a fixed set of integers. So the actual curves that are used for Ethereum don't end up looking really much like that. But it's nice to see those like that. It's quite an easy way to visualize them. And the advantage to using elliptic curves over other types of cryptographic primitives, such as RSA, is that they, in a way, they're more efficient. So for a particular size of key that you could produce in Ethereum, you get more security than the equivalent length that you would get from in RSA. Or look at another way, for the sort of standard size of key that you would need for RSA is about twice as long as the key that you need in Ethereum for the same level of security. And how this equates to the address that you have in your wallet is that you start with a private key. So here I'm talking about Ethereum, and so you start with this private key, and really this is just a random number. Now this may be derived from something else. So if you used to something like MetaMask as a wallet, you know that this may be derived from a seed phrase. So there is a concept of the hierarchical deterministic wallets, where you start off with a key phrase, and that gives you a tree of private keys that are derived deterministically. But if we start just at with one private key, from that we can derive a public key, and this is via an algorithm on an elliptic curve. And that public key we then put through a further process to give us an Ethereum address. And the process that goes through is that we take a hash of the public key, and then we take just the last 160 bits of that hash. So it's a shortened part of the hash of the public key that gives you your Ethereum address. So that's where the address comes from. There's a useful tool for trying out hashes and blocks. Let me just see if I don't know if I can. Maybe I'll leave that for you to have a look at. But it's quite nice, because what it allows you to do is to look at how blocks are produced. And I'll go through the theory about this in a second. But it also sort of explains to you about hashing and how all of the components in blocks. So it's quite a nice little demo, and for something for you to play with. Okay. But to go into a bit more detail now about the blockchain components I spoke about yesterday, I talked about a network layer and a gossip network. So this is a peer-to-peer network with this gossip protocol where we gossip around transactions and details about the network. And the messages that we are gossiping are, well, the transactions, but these represent state transitions, and I'll come on to those in a second. And then in addition to the network, we need some kind of protocol that the people who are participating in the blockchain will agree upon. We all accept this protocol when we join the network and agree that this is the way that we're going to go ahead. So we have to have some rules about what constitutes a transaction and what is valid within our system, and also details about what block is and how we create a block. You can think of the whole system as being a type of state machine, which the state machine pattern is something you've probably come across in sort of previous technology, which has an initial state. We apply some transactions, which is our state transition, and then we get a new state. And all of this is done according to the rules we have decided. And then we have blocks, so the blocks in the blockchain, which are secured cryptographically. by means of the primitives that we spoke about, such as hash functions and signatures. And these give us a history of the acceptable state transitions, the transactions in effect that we have. Then we need some kind of algorithm that allows us to come to consensus and about the state and how to decide what the next state is going to be when we get a new block. And then what I'll come to particularly at the end of this lesson is the idea of incentivization. So how do we incentivize people to behave properly within our blockchain system and to participate in our system in the first place? Why would people want to be involved in this system? And then on the more practical side, we do need some implementations of software that allow us to run a node on our network. And this is usually open source. It doesn't have to be, I suppose. And there are some blockchains such as Hedera, Hashgraph, which I don't know if it has become open source. It certainly used to be closed source. But most of the larger blockchains do have open source clients that allow you to run nodes. So I mentioned the state machine, and this is just a simple diagram to explain that. We have a state which in Ethereum we call the world state at a particular time. So here we say T, and then we receive a block which is made up of a number of transactions, and that represents our state transition and gives us a new world state. And this is repeated as we get new blocks. We just repeat this process on and on. To the question in Slido, is there a reason for taking the 160 bits? I don't know. Yeah, I don't know why that is, why they chose that number. It gives us 20 bytes address. But yeah, I don't know what the significance of that number is. It's detailed in the yellow paper, but yeah, I don't know why. Okay, so to look at the network, as I said yesterday, we have this idea of a peer-to-peer network, and the history of this came out of the sort of networks at the beginning of the century that were sort of involved in file sharing, etc. But it's important to understand that the participants in our network, there is this flat hierarchy. So the nodes are all considered really equal in the sense of the network. There's no special nodes. There's no central coordinating node that will allow people to join or leave the network. It is completely ad hoc, and in a permissionless network, anybody can join or leave the network at any time. And yeah, just no hierarchy whatsoever. And then in terms of what the nodes typically do, they will accept transactions and retransmit the transactions, but they do some validations of the transactions that they receive. So they will not pass on transactions that are not valid. So if you send a transaction to a node where you're trying to spend, for example, some Bitcoin that you don't have, then that node would detect that an invalid transaction, would drop it, and wouldn't pass it on further. And they keep a pool of transactions, which is called the mempool. And these are transactions that haven't been included in a block yet, but are waiting to be included. They are pending transactions. And then on the more sort of network level, they provide services to do with network discovery and routing. So the client has to know how to join to other nodes and how to discover other nodes on the network. And this is done via things called distributed hash tables, where the connections that a particular node makes to other nodes is not based on geographical proximity. It is based on the proximity in a hash table. So it's, you don't necessarily get connected to nodes that are close to you, but it's done with a hash of the IP address. And there is some incentivization in terms of the way that the nodes interact, in that if a node is not behaving as you would like, you will drop connections to that, and there are rules within the client software to do that. And then at the kind of software level, the node will take in blocks and update their local their local ledger based on the state transition that they have. And the way that they discover each other can be done either at initial startup. There are fixed nodes with a DNS address that they can go to, but if you've already been a participant in the network and maybe disconnected and then rejoined, you do keep a cache of nodes that you have connected to. So you will try to connect to those nodes first and discover other nodes once you're joined to the network as well. I think we've got replies to some of the questions. How would you go about sending a transaction without enough Bitcoins? So what I meant behind that was if you try to spend some Bitcoins that you don't have, that would be an invalid transaction. So that would get rejected. The other thing, I suppose, is that, as we'll come on to, when you're sending transactions into the network, you have to pay a fee. In Ethereum, this is related to gas, and so you do need some of the native currency, some of the native cryptocurrency for that network to submit a transaction. Now, that's not 100% true, and we'll see examples of how people have got around this and done things called meta transactions and gas station networks, where other people can send transactions on your behalf, etc. But that's a more sort of complex topic, and the sort of the quickest or the more generally true reply is that you would need some of the local of the native currency to do a transaction. Okay. So let's have a look at blockchain data structure. And I'd say this is idealized because each blockchain will have their blocks, the data structure of the blocks in different ways. In a couple of days, we'll come on to what the Ethereum block looks like in a great deal of detail. We'll go through all of the fields in the block and what they represent. But if we sort of looked at it in a more idealized way, a more abstract way, then what happens is you start off with the first block is usually called the Genesis block, and this will often contain configuration data about the blockchain to kind of allow the blockchain network to boot up. And then after that, you produce blocks at regular intervals. And there are two main areas in a block. There's a transaction area where we have a list of the transactions that have been picked to be included in that block. And then we have a header area, which contains a kind of summary of the data in the block. So he will have the Merkle root of all of the transactions in the block. So this is a way of kind of fingerprinting the transactions that we have. And so there will be that in there, that I've called the TX root here. There's also there's pieces of data such as a timestamp. And then the way that the blocks are chained together is that in one particular block, so say you take block 2 in this diagram, we also include the hash of the header of the previous block. So we're taking a fingerprint of the previous block header. And this is a way that we can secure the network and secure the blocks against being tampered with. Because as we shall see, when we have a set of blocks that form our chain, it is possible for these to be reorganized. And if you're running a node, you could have, maybe 1,000 blocks, and then somebody could send you, say, 100 blocks and say, oh, well, I want you to replace your most recent blocks with this 100 blocks. These are the really valid ones. And if someone did that, you would want to check that these blocks are valid. And the way that we stop people sort of changing the data in the blocks and producing and making it more difficult to produce a series of blocks that would involve a reorganization is by chaining these things together. So if somebody makes a change to, say, the transactions within a particular block, that means that the transaction root in that block's header would change. And if that changes, that means that the hash of that header would change in the next block. And so you can see that if you make even an insignificant change in one particular block, you have to effectively change all of the blocks that come after that. So this means that you have to do a great deal of work if you're going to make a change to any details that are in the blocks. Yeah, I think we've got answers to the questions. About the optimizing connections, you can, well, this is probably quite blockchain specific. You can decide to connect to certain nodes if you want to. I think by default, this is, they have this idea of the hash table to kind of randomize the connections and make the network more robust, so that we have, so it's more kind of decentralized, I suppose. But I think you can, if you want to, you can override that generally. So is this the same format for proof of stake? Well, this is just a general format, so I'll come on to the exact idea of what Ethereum looks like. There will be differences. So, for example, here I've included this proof of work nonce, which doesn't make sense in proof of stake. Every transaction has a genesis block. No, so that the genesis block is just the very first block in the blockchain. Each transaction is independent, and that's just one genesis block, but there are many transactions. And speaking of the genesis block, this is a copy of the Bitcoin genesis block. So you can see it's just a block of data. But what's nice about it, what's interesting, is that there was included in this, there's a data area that you can put arbitrary pieces of data. And so added to this, as you can see on the right-hand side, was some text, which is the headline from the Times newspaper for that particular day, or maybe a day before or so, which is talking about the bailout of the bank. So the part of the credit crisis, the financial crisis that was ongoing at the time, was recorded into the first block of the Bitcoin network. And it's quite appropriate because Bitcoin and the need for decentralized financial systems did come out of the problems that we had with the financial systems at that time. So it's quite appropriate that they had this kind of headline in there. Okay, so yeah, so that's what the blocks look like in general. But how, given that we've got these blocks and these transactions, how can we agree about the current state of a system? And the ideas for this are not go back to before blockchain. So there's research was done on computer systems in general, looking at fault tolerance. And for example, in aircraft, you have the ideas that there will be sensors in an aircraft, and there will be multiple sensors doing this the same thing. But they may start to give contradictory results, or they may fail. And so the system as a whole needs to have some mechanism that it can make sense of the system, and it can proceed, even though some of the data that it receives may be either missing or may be faulty in some way. And so this is the idea behind Byzantine fault tolerance. It's really it's asking the question of how can a computer system make progress, given that the information that it is receiving is imperfect. And it is based, the Byzantine idea is based upon a theoretical problem called the Byzantine generals problem, which is about how could a number of generals decide on whether to attack a city, given that there may be people giving them false information. And it's a sort of philosophical idea, and that's what gave the name to it. And one of the problems that we need to solve if we're designing a blockchain and we're coming to consensus and agreement about the state of our system is how to solve a double spending problem. And this really is a problem that is brought about because of the digital nature blockchains, because we're all used to being able to copy data in computers, and so if you have some digital asset, then it would seem trivial to be able to copy that. But then obviously that you don't want that to happen in a blockchain or in some cryptocurrency. You don't want people just to be able to give themselves more and more of a particular currency, or to spend a particular token multiple times. So if Alice is spending a Bitcoin, so maybe she sends some Bitcoin to Bob, how can we ensure that she doesn't then try to send the same Bitcoin to Charlie? So this is the idea of a double spend problem, and it was the big breakthrough in with Bitcoin that came. We got a practical means of solving this. Okay. Is BFT the only algorithm? No, we're going to talk about a number of those. So yeah, and I'm going to start talking now about an algorithm called proof of work. Now, there is some lack of clarity, I think, in the way that people talk about consensus. That people are not very strict, really, and they talk about proof of work and proof of stake as being consensus mechanisms, which is not entirely true. And the process that we go through really has two parts, and the proof of work and proof of stake are the initial part for that, and these are more about how we decide who is going to be a block producer, or how we do Sybil resistance, so how we stop people using multiple accounts to gain some kind of advantage. And then there's a second part to the process, which is the actual consensus part and the consensus mechanism. And this is, in Bitcoin and Ethereum, this is the Nakamoto consensus. But people tend to kind of lump them together and call proof of work a consensus mechanism, which is not quite true. And we'll see the distinction between them now. And to see how this works, it's worth considering how a transaction happens. And we can imagine we have the Bitcoin network here, and these dots here represent nodes on the network, and they are linked by these lines just in some ad hoc fashion. And we have Alice here. She's going to send a transaction to one of these nodes to show that she wants to spend some Bitcoin. She's going to send some Bitcoin to Bob. And at the bottom left here, we have this blue block represents the latest block within the system. So what happens is that Alice will send off some transaction and go to the network. And then because of the gossip protocol that we have within our network, this transaction will get passed around to other networks, to other nodes on the network. And then at some point, that transaction will get picked up and put into a block. So here I'm suggesting that transaction gets included in the yellow block, and that yellow block then is the latest block in our Bitcoin network, and that is linked to its parent block, the blue block, by the hash of the header of the blue block. So that's how it's chained to the blue block. And this process continues nicely. More blocks are produced over time. In Bitcoin, this is every 10 minutes or so. In Ethereum, every 12 to 15 seconds. But a problem we face is that how do we choose who's going to produce a block? And in particular, this is a problem because we want to get an accurate idea of the state of our system at a particular time. And what the latest block really represents is that along with previous data, but that block really represents what the state of our system is at a particular point in time. And this is the absolute source of truth for our system. So the data that is in that block and in previous blocks, that represents all of the truth about our system. And you may disagree with what that block says, but then that's unlucky, because that really is the only source of truth we have about our system. So if by looking at that block, we can say that Alice has 5 Bitcoins, then that is exactly what she has. And you cannot appeal to someone else and say that's not fair or whatever, or you want a refund, if that's the state of the system says 5 Bitcoins, that is exactly how many Alice has. But if we're thinking about how we agree what the state is at a particular time, we have a problem, because we have a situation. If you imagine this network, we could have, say, the gray transaction here has come into the network at the top left, and has started to propagate around our network. So the nodes on the top left of our network, they know about this transaction. And then the green transaction has come into the bottom right of our network, and the nodes on the bottom right know about this transaction. But how can we decide what is the correct view? What is the single source of truth about our system at this particular time? Because if you ask a different nodes, they will give you a different answer. Some will say it's the one containing the gray transaction. Some will say, no, it's the one with the green transaction. And some will say, we haven't seen either of these transactions. So we have a completely different view of the state at the particular time. Now, of course, over time, these transactions will propagate around the network. So all nodes will eventually get all of these transactions. But at one particular point in time, we still have to make this decision and come up with the state at this one point in time. And the way that we do this and decide on the state is to say, well, all of these nodes in the network are essentially equal. There's nothing special about any of these nodes. So why don't we just pick one of these nodes at random and ask them what their view is of the system at a particular time, and then we'll all accept that. If we've picked it at random, that's reasonably fair. So we'll just choose one of these nodes, ask them to tell us the state of the system, and we'll all agree that that is indeed the state of the system at that point in time. And what I mean when I say ask them to tell us the state of the system, is we ask them to produce a block, and that block kind of solidifies what the state of the system is at that time. So that seems a good way, a good fair way of doing it. But we're in a decentralized system. So how do we pick one of these nodes at random? Who does the picking? How do we do that? And that's the problem that is solved by the proof of work algorithm. And it involves a process called mining, which I'm sure you've heard of. And this is a way of picking one of these nodes to be allowed to produce a block. And what happens is that if the nodes in our network are allowed to take part in this, if they want to mine blocks, then they're allowed to do that. This is a permissionless system. But they don't have to. You don't have to be a miner in the network if you don't want to. But if you do, what you do is you run special mining software, which includes you in a kind of a race or a lottery. And this is what you need to do is to solve a mathematical puzzle. And what happens is, if you imagine the starting point is the point at which a previous block has been produced, from that point on, all of the miners in our network then are involved in a race to produce the next block. And to do this, they have to produce a puzzle. And this is a mathematical puzzle, and it involves a hashing algorithm. And what the algorithm, how the algorithm works, is that you take data from the block that you're going to produce. So the miner, first of all, sort of starts to create its block that it wants to produce and to propagate it throughout the network. And it has the data in there, it has transactions in there. So it starts to produce that. And then from that data, it has to solve a puzzle. So part of the puzzle involves the data. So in this example here, I've represented the data by the phrase "hello world," and then to that it adds a random value. So here I'm just adding random numbers. And what it does is that it takes this as the pre-image, as the input to the hash function. So it has this piece of data, it appends to this some random value, and then it takes a hash of that. And then to solve the puzzle, you have to have the output of this hash function below a certain number. So it has to be below a number that is represented by something called the difficulty. And the way we typically call about that, typically we represent that, is to talk about the number of zeros that are produced in the output of our hash function. So here you see an example, and this is really a small example, a toy example, but we have an example of a would-be miner here who is going through, taking data from the block. In this case, we've just got this string hello world, and adding random numbers to it and trying these out to see what the output of the hash function is. And eventually, as it gets to the number 4250, it has one that has got 4 zeros at the beginning of it. Now, in actual fact, the 4 zeros wouldn't be enough to be the answer to the puzzle in something like Bitcoin. I can't remember what the current value is. It used to be about 19 zeros, so it is an incredibly small number. And that's one of the features about this puzzle, is that it is incredibly difficult to solve. What you're trying to do is to find this random number that will give you an output when you've gone through this hash function that is very small. But to do that is incredibly difficult. And all of the miners in Bitcoin are making literally trillions of guesses per second at this number. They're trying this out trillions of times a second. And there are tens of thousands of people doing this in the network. And yet it still takes, on average, 10 minutes for one of these miners to find one of these random values that, when put through the hash function along with the data, produces an output that is small enough to be considered a solution to the puzzle. So that's the puzzle that we go through to be allowed to produce a block. And if you go through this puzzle, if you manage to solve this puzzle and get a number that is small enough, then you can produce a block. And what you do is you've already put together the details of your block, and you add into your block this random value. Let me just go back. Oops. Here, so you add in this proof of work nonce. So this is the random value that you've guessed. This is the solution really to the puzzle. And once you've done that, then you can send your block out to the network, and the other participants in the network can verify that that is indeed a correct answer to the puzzle. And the useful thing about this hash function is that although it is very difficult to solve this puzzle, to go one way is very difficult, takes lots of time, and you can only really guess at the value you need. To verify that this is a correct value is very quick. It's done in milliseconds. So it's all of the other nodes on the system can verify very quickly that the miner who sent out this block has indeed solved the puzzle correctly, and this is a valid block for the network. And the miner is incentivized to do this because if they manage to solve this puzzle, they can then also create a transaction to pay themselves a reward, and this is called the block reward. And so they will add a transaction at the start of the transactions in the block, and this is called the Coinbase transaction, where they pay themselves a certain number of Bitcoin. So this is a financial incentive for people to do the mining. They also get the additional incentive that the people who have sent transactions into the network are paying transaction fees, and the miners claim these transaction fees. So the transactions that they include in the block, the fees for those transactions are then claimed by the miner. The questions about difficulty I'll come on to in a second, and also what happens if two miners mine the block at the same time. Why would nodes disagree on the final state in the first place? Well, this is the problem that we get here, in the fact that the state of the network could be different for different nodes on the network. So because there's time is taken for transactions to propagate across the network, different nodes will have different views of the state of the system at a particular time. So that's why they would have different ideas. So the difficulty of solving this puzzle is adjusted over time. And this is done according to the rules of the protocol. So everybody who participates knows how to adjust the difficulty. And it's adjusted so that the block time remains roughly constant. So what happens is, if we're producing blocks and we're solving this puzzle, if it takes us consistently more than 10 minutes to produce a block, then the difficulty is seen as being too high, and so the difficulty will be lowered. And then if we're producing blocks too quickly, then the difficulty is seen as being too low, and it will be adjusted upwards. And this is done according to an algorithm that is part of the sort of the protocol of the system, so that the miners and all the people involved in the system all understand how to calculate the difficulty at a time, and would reject blocks if a particular miner tried to change the difficulty to something that was invalid, then any blocks they produced would get rejected. And this graph here shows the change of difficulty over time. And what happened was, this was from last year, where a lot of miners a lot of mining was done in China. And then at a particular time, this was made, laws were passed against this. And so a lot of the mining in China was shut down. So suddenly there were fewer people mining. So it was taking longer to produce a block. There were fewer people solving this puzzle, so the block time increased. And so as a result, the difficulty was dropped down until we got to a situation where the block time was roughly 10 minutes again, and then we could continue. So it is dynamically adjusted over time. And it was assumed when Bitcoin started that over the years that the hardware involved in solving this puzzle would get more efficient. And so that's why we have the ability to change the difficulty. It was assumed that otherwise the block times would decrease because of improvements in hardware. So even though we're able to solve or make more guesses at the puzzle and effectively solve it more quickly because of the hardware, we adjust the difficulty to increase the difficulty of the puzzle so that we keep the blockchain, the block time constant. The question about how many transactions to include in the block, this is up to the miner. So the miner is in control of how many transactions and which transactions they include in the block. And we shall see in later lessons how this gives the miner a great deal of power and how this can give them certain financial incentives. So yeah, it's really up to them how many transactions they want to include. But remember that they get a reward for each transaction that they get include in the block, because they take the transaction fee for that transaction. So it is generally in their to their benefit to include as many transactions as possible, or maybe the ones that are paying the highest fees. Okay, now to go on to the second part of the mechanism. So I said that proof of work was really about choosing the block producer, and that's really not the consensus mechanism. The consensus mechanism is the part that I'm going to talk about now, and this is called Nakamoto consensus. And this solves the question of what do we do if two miners produce the block at the same time. So we could have this situation. So we've been going along, we've produced the yellow block, and then because it takes time for blocks to propagate across our network, we could get the situation where the red block was produced without knowledge of the green block, and the green block was produced without knowledge of the red block, and they were sent out across the network to all of the other nodes. And then the other nodes have the problem of how to decide which one of these two blocks to include, and which one is the canonical block, which block should form the next one in the chain. And the way that the Nakamoto consensus does this is really a kind of a heuristic. There's a rule of thumb about this, in that there is always a way to decide which one of these blocks to include. And it's to do with solving the puzzle. And both of them have solved the proof of work puzzle. But we look at the kind of the amount of computation that has been involved in that, in addition to all of the previous blocks. And this is often called the longest chain. So we kind of say we're going to take the chain that has not just the most amount of blocks, although it probably will be that, but also where we can see that the most amount of work has been done in producing these blocks. So any particular node on this network will be able to come to a decision about which one of these two blocks it would accept as being the latest block. And so we would then, in this case, we would say this is the red block. So the decision has been made that the red block has done the most work. And so the next miner would then use that as the basis to produce the next block, produce the beige block. And the parent block for the beige block would be the red block. And then we would just carry on. And the produce blocks. And at this point, once we've produced the beige block, then obviously that is obviously the longest chain. We've got more blocks there. But it could be the case that later on, a number more blocks could be produced, and we could have what's called a reorganization, where we could find, we could drop some of these blocks and then introduce other blocks to produce the longest chain. And we shall see how that works in a second. But I should say at this point as well, the green block, if we're talking about Bitcoin, the green block here is what's called an orphan block, and it just gets completely dropped. Sadly, for the miner who produced that block, they don't get the block reward, because effectively the transactions within, or that block is not really this part of the truth about our system. And the transactions within that block, although they're not sort of included in the as the green block, they may well be included in the red block. So we don't really lose data. So transactions that were in the green block will end up being in other blocks. So because the nodes all have these mempools where they store transactions that haven't been included in blocks, you would never get the situation where you would never get the situation where transactions are dropped because of a block being orphaned. Those transactions would always get picked up and included in other blocks. So the only real downside to this is for the miner of the green block. So he doesn't get his block reward. The red miner gets it instead. But other than that, it really makes no difference to that. And in terms of the question, does this happen often? In Bitcoin, it doesn't happen that often, and a couple of times a day maybe. In Ethereum, it happens much more often, and this is because of the block time. So it's a kind of a trade-off between the time it takes to produce a block and the time it takes to propagate a block across the network. So if you're producing blocks very rapidly, then there is much more chance that two miners will produce a block at the same time without seeing the other block that was being produced, because the time taken to get that block across the network is much more significant. With Bitcoin, when we only see one every 10 minutes or so, it is less likely to happen because the time taken to propagate the block is less significant compared to the 10-minute block time. No, so it's not the case of the number of transactions to win the Nakamoto consensus. It's to do with the amount of proof of work that was done and how well the puzzle was solved that then wins the Nakamoto consensus. Okay, so that's describing the proof of work algorithm and the Nakamoto consensus. This is the basis for how Bitcoin and Ethereum produce their blocks, and the advantage that this gives us, and while we're doing this, is that this gives us incentives to prevent malicious behavior, and we're getting real economic incentives to stop people doing malicious things. And the incentives are from the block reward, so the miner will get a reward for producing the block, but to do that, they have to do some work, and they have to really invest in the process. The computation that is involved in solving this mathematical puzzle is quite significant, as we'll see in a second. In the amount of energy that is involved in doing this is significant, and it has a very high real-world cost. And the the cost of Bitcoin is tied into this to some extent, because if you're going to mine on the Bitcoin network, you'll want to be sure that the reward you get when you produce a block will cover the cost that you have to solve this puzzle. So the cost of doing this computation. And the reason I say this work is useless, that's also important, because if the work that was being done as part of this mechanism had some other use, if it was valuable in some way, this would alter the incentives. So it wouldn't just be the case that the incentive is completely from the block reward and the transaction fees. Then there will be other incentives about doing this work. And this would then sort of skew the way that Bitcoin works. So it's important for the way that Bitcoin works is that this work is essentially useless. It really cannot be used. And we're just solving this puzzle. We're just doing trillions of hashes of effectively random data when we do this. And it really doesn't have any use unless you want to collect the outputs of hash functions for various inputs. If you want that, then yeah, so miners are doing that, but generally they're not storing this. I mean, that would be expensive also. So they do these hashes, they test whether that solves the puzzle, and then they throw that away. So it's not kept. So it really is useless. And this forms the basis of the security of Bitcoin and Ethereum. It's this economic incentive and the investment that people have when they're producing blocks that incentivize people in the right ways to behave in the right way in the system. And you should contrast this with the way that traditional banks work or centralized systems work, where they have to add in lots of layers of security and authentication, all sorts of things to prevent people doing malicious things within their system. Whereas in Bitcoin and Ethereum, these are completely open. Anybody can get involved and do what they like, but the incentives to behave properly are completely cryptoeconomic. And we'll go on to the cryptoeconomics towards the end of the lesson. So the question is how to determine which block has more computational power involved. So you can look at when the puzzle is solved, you can look at how well it was solved. So if your criteria for solving the puzzle is that it has 19 zeros in front of it, if you have 19 zeros, then you've solved it. Great. If you come along with 30 zeros in front of it, that is considered even better. So that's how they consider how would they work out this computational power. It's not exactly true, but it's a rule of thumb for trying to work it out. Okay. Now, if we talk about security, we can look at the types of attacks that can be made upon networks. And the one that you may have heard of that applies to networks such as Bitcoin and Ethereum are 51% attacks. And what this means is that, or what this is about, is if you imagine one person or some entity having so much computing power that they had as much hashing power available to them as it made up 51% of the network. So if Google and Amazon all joined together and got all of their servers that they had trying to solve this proof of work puzzle, they may end up with sufficient hashing power to be more than the rest of the participants in the network put together. And the question is, if they did that, what would that allow them to do? So that's something you can ponder for a second or so, although the answer is on the next slide, because I'll go through an actual attack of what they can do. But we're particularly interested in, could they do a double spend, or could they put through an invalid transaction? So 51% attacks certainly have happened. And it is something that people who design blockchains, such as Ethereum and Bitcoin, have to be aware of. They have been done mainly on other blockchains, such as Ethereum Classic. And that's what I want to explain about now. And this is an actual attack that happened on the Ethereum Classic blockchain. So this was a blockchain that split off from the main Ethereum blockchain. So it was similar to Ethereum, but it split off and became a completely separate blockchain. And the important point about it was that it had fewer miners than the main Ethereum blockchain. So it had less hashing power. So it was easier for someone to go into to join the Ethereum Classic network and to effectively get 51% of the hashing power of the network. And what it allows you to do, if you have this much hashing power, then what you can do is you can be confident that when you're trying to produce blocks, that you will consistently win this race to produce the next block. So every time we're trying to produce a block, it is really random who will end up producing that block. But if you want to stack the odds in your favor, then if you have more and more hashing power, then it is more and more likely that that is going to be you. And so if you have sufficient hashing power, then what you can do is present an alternative set of blocks to the network. And that alternative set of blocks will need to have sufficient computation within them that they can replace the existing set of blocks. So what the attacker is trying to do is to give the network a series of blocks and show that these blocks have more computation being done in them than the accepted set of blocks that were forming the canonical chain at that point. And then the nodes on the network, seeing these new sets of blocks, will then replace the blocks that they have with this new set, because this new set has more computational power or computational work done in them than the original set of blocks. Because of the way Nakamoto consensus works, because we're choosing the blocks to include in our network, depending on which ones have the sort of more computation done in them. So if you come into the network with a set of blocks that have more computation, then effectively you can create a large reorganization. And this is what happened with Ethereum Classic. So just to talk you through the way this worked, the blue blocks here represent the original canonical chain that were produced by honest miners. And what someone did was to create a double spend. And this happened on, say, block 22. And what the malicious miner, the one who is producing the red blocks, he did was he started mining and started producing blocks for himself, but didn't release these to the network. And what he did was on block 22, he did a transaction to an exchange, and he effectively sold 100 ETH, Ethereum Classic, ETC, 100 ETC. He sold that to the exchange, and and the exchange then gave him some fiat currencies. So it was about $100,000, I think. So in block 22 or just afterwards, we got the situation where there was a transaction that moved 100 ETC from the attacker's account to the exchange account. And in return, the attacker got his fiat currency. And so that was fine. And the blue blocks continued being produced, all showing that the state of the system now meant that the attacker had 100 ETC less. But what the attacker was doing while this was happening was producing his own blocks, but he either invalidated that transaction in the block or he missed out that transaction in his version of the blocks. And then about 100 blocks further along, what he did was he introduced these blocks to the chain, which meant that all of the participants in the network reorganized their canonical chain. So they changed the truth about the system at that point. But the truth about the system now changed to be with the truth that was in the red blocks. And in the red blocks, this transaction, which sold his ETC to the exchange, never happened. So suddenly he still had his ETC, he still had his cryptocurrency, but he also had the fiat currency that had been given to him by the exchange. So effectively, he'd done a double spend. And this is the classic way of doing a double spend attack. And he got away with this. And although he did return some of this, and when we talk about security, we'll come across this quite often, the quite strange notion that attackers often return some or all of their ill-gotten gains to where they got it from. And sometimes they give reasons for that, and yeah, sometimes they don't. But anyway, he did get away with a certain amount. I don't know how much that was worth, but he got away with it because he was able to effectively change the truth about the blockchain by introducing these extra blocks. And this has been done on a number of blockchains, but it's not always been done for malicious purposes. There was the case a number of years ago with one of the Ethereum test networks that it was being spammed, and there's lots of problems with it. And the kind of the good guys, the sort of the Ethereum devs and people who wanted to try and keep this network going and stop all of this spam and spurious transactions on it, what they did was they got enough computing power together to kind of present an alternative view of the test network blocks that got rid of all this rubbish. And then they dumped those onto the test network, and everybody reorganized their chain that got rid of these spurious transactions. So it sorted out the test network, but it was done for, you know, the good purposes rather than malicious purposes. Now I'll show you this. This is not completely up to date. I took this a few months ago, but it's a website that you can go to, and it tells you the cost of doing a 51% attack. Now, please don't do this. I'm not showing you this to suggest that you should do this in any way, and please do not do this. It's just to illustrate to you that this is possible, and to show you how possible, the effective cost of doing this, and to show you that networks are vulnerable to this. So Bitcoin and Ethereum, if you look here, it shows you the amount that it would cost to attack this in terms of running certain servers for a certain time. And the top few are generally seen as being beyond the realms of doing an attack. But as you drop down, you'll see that some of the networks they are much more vulnerable to this process. So, for example, Bitcoin Gold there, if you spend $2,000 on compute power, then you'll have enough hashing power to get 51% of the network. And this is a big problem for smaller blockchains, is getting enough honest miners involved in their blockchain to prevent a 51% attack. Oops. So why do we use proof of work? Well, when it was introduced, it solved the problem that it was a feasible approach to creating a blockchain, and it was quite easy to understand. If you model this mathematically, it's not too difficult, and it's easy to implement. It's easy to do a hash function, and it has worked very well. It has secured the Bitcoin network for more than 10 years, and the Ethereum network for 7 or 8 years now. And it has been very robust, despite the fact that people have tried to exploit it. But it has disadvantages. To go through some of these, there has been some centralization. With Bitcoin, you can buy specialist hardware to do mining, and there is centralization around that because only a few companies produce this. So it is really centralizing who is involved in that sense. There is a centralization of hash power as well. People come together and form pools to do hashing, to do mining pools. And this photo here from a few years ago, but these people here, represented over 90%, I think, of the hashing power of Bitcoin because they were in charge of these different pools. Now, in effect, they're in competition with each other, and so the fact that the so few of them is maybe not too problematic, but there is centralization. There was geographical centralization, particularly in China and areas where energy is cheaper. You tend to get centralization and lots of mining happening, which can be seen as problematic. And certainly one of the things that people pick up on about Bitcoin is the cost that this has in terms of the energy. So there's a great website, the people who do research into this, the Cambridge Bitcoin Electricity Consumption Index, and they have this kind of headline figure about where Bitcoin's fits in amongst energy usage of other countries, and you can see there where it is. So it's using more energy than Ukraine at the moment, and it's sort of coming up to Egypt. This is really a headline figure, though, that people pick up on. The actual truth about this is perhaps a little bit more nuanced as well. So I wouldn't just take that. If you're thinking about this, go have a look at their website and learn more about it. The diagram on the right there shows where Bitcoin compares to other types of industries using energy. So it's what do we have there? So it's using less than iron and steel, or producing paper, etc. Yeah, I think is it less than, I don't know, more than lighting, but certainly less than air conditioning. So there are a number of different factors involved here. So and then, as I say, there are other mechanisms, consensus or Sybil mechanisms. So one of the first ones that came out, before blockchains, because people were looking at consensus generally in systems, was PBFT. So how to make decisions on systems, how to come to consensus. Nakamoto came out in 2008, and then in terms of choosing the block producers, there are many alternatives to the proof of idea. So we have proof of stake, proof of authority, history, burn, blah 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 blah. And I was even involved, or XP was even involved in one called proof of kernel work. There's a link to our paper there if you're interested in that. It's not a simple thing to do. Obviously, you have to get all of the incentives aligned correctly, but it's certainly an interesting thing to have a try at. So one of the alternatives to proof of work, and the one that Ethereum is going to move to, is proof of stake. And there are many different ways to do this. The general idea behind it is that rather than solving a mathematical puzzle to pick the block producer, you have some other function to do that. So you have some other way of doing that sort of picks someone at random. But the people that are picked still must have some sort of stake in the system, because with proof of work, they've got the stake because they're doing the work. So you need something similar to that. So that's why we need to have a stake in the proof of stake system. And so they submit a stake in the native currency of the system, and that allows them to be considered to be a block producer. And then they're chosen at random, but the probability of being chosen depends upon the size of the stake that you have given. And then if they do something malicious, then they will lose their stake. So it is, there's quite a disincentive to behaving maliciously. And one example of this is with the MENA protocol that we'll talk about when we talk about zero-knowledge proofs. But this is a really interesting blockchain. It uses a proof of stake. Well, it's based on the Ouroboros consensus mechanism, which came from Cardano, and it uses proof of stake to pick a block producer. And I should say, for for transparency here that XRP is a block producer on Mina. In fact, we produced a block earlier today, and it is done via this process. So the process of you being picked to be a block producer, depending on putting up a certain stake. And then you can produce a block. It's slightly different to something I'll come on to called delegated proof of stake, because the participation is open to anyone, and there's effectively an unlimited amount of people that could be block producers. It is different from Cardano because you don't rely on long-term history, and there are other sort of nuances as well about the way that staking works. But there's some links there if you want to find out more about it. I'll just mention PBFT briefly because we're kind of running out of time. This ends up being a lot more complex really than something like proof of work. And one example of this is called Istanbul, and it involves nodes voting on proposals and coming to consensus by voting and working out which proposal has the most votes. So there are a number of rounds that happen when you want to produce and accept a block. So this gives a diagram of the number of rounds involved. And the problem with this sort of procedure is this voting process and the fact that all the nodes have to get involved and that there has to be a 2/3 majority to agree on things. So as you try to scale this system, as the number of nodes involved in the system increases, this whole thing becomes much more difficult, because then the amount of messages that need to go back and forth to do all of this voting increases and makes the whole thing much more difficult. Delegated proof of stake. So yeah, I mentioned that just now. So the idea behind this, it's similar to proof of stake, but other people can delegate and vote for who will be a block producer. And there are some systems such as EOS that do this. One of the drawbacks to this, and particularly if you look at EOS, you find that there are only 21 block producers. So there is some centralization happening. And there is also the possibility, now I don't know if this was in EOS, it may have been in a different chain, but we did get a process happening where, because of the voting, the way the voting worked, that the people who were in this top list of block producers, they would vote for each other. So they would come to a sort of agreements between themselves to vote for each other, and thereby they would keep their position in this list of block producers. So it stopped the process being as dynamic, but it's certainly a process that has worked reasonably in some blockchain systems. Okay, just to go through questions. Why can't you train transactions? Yeah, that's a very good question. So I guess the way putting it in blocks maybe makes it simpler. We can look at some examples. So if you look at things like Solana or IOTA, they have a different process where instead of having blocks, they have these things called directed acyclic graphs, where the transactions effectively are sort of linked together in certain ways, and that is more sort of similar to what you're asking. But it is difficult, and it has taken a number of years for this to be done successfully, and certainly with IOTA, they needed a coordinator to help this to proceed, and they did have problems. The block producer, do they still need to do some? So yeah, it depends. There are different ways to do the picking of block producers on proof of stake blockchains. It can be done in different ways. So it really depends upon the blockchain that is in doing that. We'll just quickly talk through something about cryptoeconomics, because this is quite a new field that came about because of blockchains, and I guess really was probably invented by Vitalik really, and or Vlad Zamfir. But it brings together sort of economics and the cryptography and looks at the incentives and the process by which blockchains work, and how they make robust systems, and how they make systems that are resistant to various types of attack. And there are certain things that you want to encourage in systems. I won't go through them. Actually, part of the homework, in fact, part of the homework looks at this, and the question you have about a 51% attack in proof of stake, that's also part of the homework. So I'm going to avoid answering that question. That's something for you to think about in your teams. But if we look at, if you imagine you're inventing a cryptocurrency, there are certain things certain properties about it that you may want your cryptocurrency to have. So I can talk about those here, or give some ideas of the terminology. One idea is this eventual consensus. So with Nakamoto consensus, it is thought of as being eventual because we have this possibility of reorganizing the chain. This canonical chain can be reorganized, but the cost to do that grows over time. So certainly on Bitcoin, we can add a new block to the chain, but if we tried adding, and that will have a certain cost. If we try adding 3 blocks, that will have much more cost because there's much more computation being done in 3 blocks. If we wanted to add 1,000 blocks, that would be a huge amount it would be hugely expensive for the person who was doing that. And so even though in theory that is possible, that the consensus could change, and we could have 1,000 blocks being reorganized, the chance of that is incredibly small. And so that's why the consensus is called sort of a eventual consensus, because over time the possibility of the consensus being changed goes down very rapidly. And yeah, that's really what the confirmations is about. The thing called liveness is important to think about, because this is needed because we want our blockchain to keep working. We don't want to get to a situation where the blockchain will stop and we don't know how to produce another block, or we don't know how to choose which block is the latest block in our system. And there have been examples with blockchains where this has happened, and it's been quite problematic because the protocol for your blockchain is agreed before the blockchain starts and has to be agreed by everybody in your system. And to change that, as we shall see in a moment when I talk about governance, is not a simple process. So if your blockchain stops, you're in real difficulties, because you can't really easily change the properties of your blockchain on the fly, or in order to deal with that kind of situation. So you have to think about this idea and think about these kind of problems in advance. And the idea of fairness, really, that comes back to this idea I said, where we would, if you, when you're picking somebody to produce a block, you want it to be done at random. You want it to be seen really to be fair in that sense. I'll just go through these very quickly because we are running short on time. But the way that we influence behavior in blockchains is via cryptoeconomics and via certain types of incentives. And I've linked to some articles here. You can read more about this. But you have to get this worked out and aligned and calculated properly before you start your blockchain. And you can incentivize in 2 ways. You can give people rewards, such as the block reward or the transaction fee reward, or maybe you give them privileges within the system. Now, in Bitcoin and Ethereum, these are permissionless, but in some systems, there are permissions, and different participants may have different roles. So it could be that you incentivize people by allowing them to take on a particular role in a system. And then on the flip side to that, you can have punishments. So you might have a direct punishment, such as the loss of a stake in the system. If so for example, in proof of stake, or if you have a privilege in the system, a particular role, maybe you would lose that role if you behave maliciously. So two ways to incentivize behavior. Some of the terminology you may come across in economics, I'll give some of the meanings there. So it's all about, things like the economic loss that you would get if you do a certain behavior, and being able to quantify that. And in the crypto, if you're working out the cryptoeconomics of a system, you want to know that the loss that somebody would get if they behave maliciously is far more than what they could potentially gain. And when people are working out, for example, proof of stake systems, they have to go through this idea and work out the cryptoeconomics very carefully to do that. And that all sort of ties into game theory as well, and working out, the game theory. And you do assume that you generally assume that people are acting in their own economic interest. That's not entirely true, I suppose. People may try to wreck your blockchain just for the fun of it, and they may do this at an economic disincentive to themselves. And we'll see when we talk about security in our smart contracts, we will consider this, the fact that people might try to break your contract not for an economic gain, and they might try to do it even though it will cost them money, but they may do it just for the fun of doing it, or just to try to break your system. And hopefully, if you get all of this correct, you will come up to some kind of equilibrium point. So you will get equilibrium in your system where the people are behaving honestly, and where if people behave dishonestly, then they don't have any progress in your system. Interesting points from an article there about the way that the scaling happened with Bitcoin, and how that's happened to do the cost of verification. So the fact that when nodes on the network receive a block, it is very simple for them to verify that that block was produced correctly. They can verify quite easily that the transactions are all the transactions that are included add up to the Merkle root of the transactions. They can show that this block has the correct parent, the correct hash of the parent header in the block. They can check the nonce, this guess that they made at the proof of work algorithm. They can check that very easily. So all of that being able to be done easily and efficiently has helped the Bitcoin network to expand and to scale. Okay, but if we, I think if you look at blockchains and what people say the problems are with blockchains, most people would say scaling is the big problem, and they'll say, well, Ethereum can only do 25 transactions per second or whatever, and Bitcoin is only 7 or something like this, and that's the big problem. But another view certainly is that governance is also quite problematic for blockchains, and there's a link to an article there that you can look at that. If you want to look into governance, you can look at this in a number of areas. So who is involved, if the people that are involved, how do they get the information that is needed to be meaningfully involved in the system, and then how do you incentivize people to be involved in the first place and to behave correctly, and then for the governance, how what procedures are in place to actually do the governance. And what I'm talking about here is, if you have a blockchain, how do you change the protocol of that blockchain over time? So, for example, someone mentioned in one of the questions about the block size wars with Bitcoin. How do you how does that debate happen? How do you decide what the block size is going to be in Bitcoin? And the are two sort of aspects to this, or two ways of approaching this. You can have your governance mechanism on chain, which is thought of as quite an advantageous approach, because it's quite efficient. The communication is quite efficient, and the sharing of information is quite efficient. Off chain is much more ad hoc and less efficient. People may not know how to get involved, or where the information is, or may find it difficult to be involved. And typically, with off-chain communication, you often find that the developers start to dominate the governance process. Now, one blockchain that has really prioritize the idea of governance is Tezos, and they have an on-chain governance process which people can get involved in. They incentivize people to be involved. You can vote on changes to the network, and then those changes are automatically applied once as votes are taken. If governance fails, what you get is usually a hard fork, so the network will split, as happened with Ethereum and Ethereum Classic. There was a change to the network to cope with the DAO attack, and then some people agreed with that, some people didn't. The people that didn't agree formed their own network called Ethereum Classic, and these networks diverged. It's interesting. This chart is interesting. This was from the Bitcoin and Bitcoin Cash divergence. What happened? This illustrates how the difficulty happened. So the two networks split, and initially the Bitcoin Cash, the new network, had very few miners, so the difficulty dropped way down, which meant that it was easy to produce a block. So then miners from the original Bitcoin network all moved to Bitcoin Cash because they could produce blocks more quickly, get more money. So then that pushed the Bitcoin Cash difficulty up and pushed the Bitcoin network difficulty down. And you got this sort of seesaw effect of miners swapping back and forth as the difficulty seesawed back and forth. If you go to this site, fork.lol, you'll see this kind of thing, although the process has settled down a bit now. So yeah, almost at time. So hopefully that was an interesting look at the blockchain components in more detail, particularly the consensus mechanisms. And I went through very quickly the cryptoeconomics and the governance as well, but we can come back to those and go in more detail. And just one of the questions on Slido. Yeah, the questions and answers are archived. So yeah, I think you can see the archive tab. So they are saved there, but we can also distribute them as well. Okay, so next lesson, we're going to get some hands-on practice because we're going to start with Solidity. So less theory and more practice, more coding. Which is good. So I'll finish there. Please continue to ask questions, and thank you. Thank you for your comments. Yeah, an interesting one. Laura Shin talks about the hacks. Yeah, so the DAO, the attack on the DAO and the identity of the hacker was released in that book. So a very interesting book. Yeah. Anyway, yeah, thank you, everybody. I'll stop sharing now. I have put the homework onto the Discord channel, so please have a discussion about that in your teams. And I look forward to seeing you tomorrow and doing some Solidity. Thanks, everyone.
Thank you, everyone, for your attendance. If you have any questions, just feel free to reach out to me on Discord. And yeah, and also be active in the channels. If you have any questions, do put them there as well. So thank you, everyone, and have a great rest of your day. See you tomorrow.